Hi, welcome to the AICE Chemistry lecture series. This is chapter 3, section 3. And we're going to be looking at accurate relative atomic masses, which is a continuation of a topic that we did in honors chemistry, where we looked at how to calculate the atomic mass of a compound or an element based on its isotopes. Now, in this section of the chapter, we're going to go more in depth into that and not just look at how we calculate the atomic mass, but also how do we figure out the relative isotopic masses of the isotopes as well as their percentages. So we do this by looking at what we call a mass spectrometer. A mass spectrometer is a machine specifically made to separate things with different masses. And we can use it both for isotopes as well as organic compounds. There is a section at the end of this chapter on organic compounds, but we will leave that until chapter 18. So that is the only section where we're going to skip from a chapter because it makes a lot more sense to look at this section once we do organic chemistry later on. So let's look at mass spectrometer in the light of isotopes. A mass spectrometer is a tool that we use to measure the mass of each isotope present in an element and the relative isotopic abundances. Now, if you remember, we call the mass of an isotope relative isotopic mass, and that's what we're measuring here with this tool. But the relative isotopic abundance refers to the proportion of one particular isotope in a mixture of isotopes, usually expressed as a percentage. So it's essentially what percent of all of the atoms of this element are each individual isotope. Now, you don't need to know how the machine works, the mass spectrometer works, but I think a basic understanding of it is helpful. Essentially, what we do is we introduce some kind of element into this machine, and then it gets vaporized with high heat, and ionization happens in this chamber. What ionization essentially means is that we are going to knock off some electrons from this atom so that they are all positively charged. Now, the positive charge doesn't matter. It's what we do with it that matters. When we grab this collection of atoms, let me use a different color. When we grab this collection of atoms here, so we have some isotopes of one mass, and I will make those in pink, some isotopes of another mass, and we'll make those in red, and then some isotopes of a third mass, and we'll make those in blue. That was blue, this is red. When we have those three different isotopes and we make them all positive, and then we throw them, we use magnetism to speed them up and put them through these electrodes that are positively charged. Well, that's what I'll do. It's going to speed them up through this machine, and a magnetic field makes them turn. Well, the isotopes with a heavier mass, when they go through this machine, will turn a lot more slowly. So in pink, we have heavier isotopes, ones with larger masses. Those with a lighter mass, let's make the lighter mass blue, will turn a lot more because they're easier to turn because their masses are lighter. So we'll say that the blue are lighter. And then the red, we'll call them medium. So if they have a mass in the middle of those two, then the red ones will turn less than the pink ones, but more than the blue ones. Essentially, we use that ionization, making them positive ions, to make them be able to be affected by a magnetic field. And then once they turn due to the magnetic field, depending on their masses, the heavier ones will turn less because they're heavier, so it takes a lot more force to turn them, whereas the lighter ones will turn more because they're lighter and they don't turn as much force to turn. The medium ones will turn somewhere in the middle. So there's a detector here at the end that when we use this detector, it can detect where these isotopes hit and how many of them are hitting. So we get the mass from how much they turn, and we get their abundance by how many of them hit the detector at those three individual points. How many of them hit here, how many of them hit here, and how many of them hit here. And that's how we get the abundance. The more of them hit there, then the more red ones we have, the medium mass isotope. The more hit here, the more of those lighter isotopes we have, so on and so forth. So that's the basics of how a mass spectrometer works. Again, this is a very complex machine, and you don't need to know how it works, but I do think it's a valid way of kind of reasoning what you're looking at with the mathematics. So let's move on to the next slide. So how do we determine the mass? And this is from honors chemistry. We determine the atomic mass, the AR, of an element by using the data from the mass spectra. We are going to use both the percentage of its isotope and the isotopic mass of the isotopes to figure out the relative atomic mass of the element. We multiply each isotopic mass of each isotope by its percent abundance. Then we add them together and divide by 100. So why these steps? We multiply each percentage of the isotopes times its isotopic mass because the atomic radius, the atomic mass is a weighted average. Now, what is a weighted average? Because that is an important word. And we looked at this when we looked at, I don't know where that one went. So it's a weighted average. We looked at this whenever we looked at the definitions of different masses, right? A weighted, the relative atomic mass is a weighted average, meaning that not each one of the isotopes is given the same amount of weight. Is not given the same amount of influence on the atomic mass. An isotope that is more present, an isotope that has a higher percentage, is going to have more of an effect on the atomic mass than an isotope that has a much lower percentage. So in order to do this mathematically, what we do is we multiply the isotopic mass of the isotope times its percentage. Now, what does that do? The higher the percentage, the more of this mass we keep. The lower the percentage, the less of the mass we keep for the atomic mass. So this little part of the equation right here where we multiply the isotope's mass times the isotope's percentage, that's the weighted part. That's where we make each isotope contribute differently to the atomic mass based on its percentage, how common it is. So we do that for each isotope, we do it separately. So there's 5 isotopes, we do 5 times. So there's 3 isotopes, we do 3 times, whatever. And then we add those numbers together. Then we add them together to kind of get that isotopic mass. But before we do that, we have to divide by 100. Why do we divide by 100? This is the part you have to be careful with, depending on what you're doing. If we're using the percentage, then we divide by 100, because when we use percentages in mathematics, we use them in their decimal form. So you could approach this in 2 different ways. We could divide by 100 if we're using the full percentage, or we could not divide by 100 if we're doing the decimal version. So for example, if we had 50%, right? 50% in its decimal form is 0.5. 25% is 0.25 because we divide by 100 to get the decimal form. That's what percentage means. If we had 10%, that'd be 0.1. If we had 1%, that would be 0.01, so on and so forth. So if we're using this side, if we are using 50 or 25 or 10 for our equation, then we would divide by 100 at the end of our equation. If we're using this side, however, if we're using 0.5 or 0.25 or 0.1 for our equation, we do not divide by 100. The equation as it's written here, that divided by 100 is if this is in percent mode. Meaning that if it's a full percentage. We don't do this part if we're using 0.5, 0.25, 0.1, the decimal version, because we already did that and that's where those decimal versions came from. So be very careful with that. And it doesn't matter which way you do it, the AICE exam, you'll get full credit. but you have to be very careful and make sure that you are being consistent and that you don't divide by 100 too many times. So let's go to the next slide. So now the difference between honors and AICE chemistry is that when you were given the data that you needed to use in honors chemistry, you were just given the pure data. You were just given the masses and the percentages. In the AICE exam, you might be given what we call a mass spectra. A mass spectra is the data, the graph that comes out of the mass spectrometer we talked about earlier. So the mass spectra looks like this, and it can be very daunting to see graphs and charts on these questions, but it's actually fairly simple graph to read. So the mass spectra has x and a y-axis, like most data charts or data graphs. We have the relative abundance on the y-axis, and what this is the percentage, just how high the percentage is. And then we have the mass to charge ratio on the x-axis. So let's go into those. So the y-axis is the relative abundance. What percent of all the isotopes have this mass, right? And that's just gonna be the relative abundance for the isotopes. Most of the time, this relative abundance is in percentage, so 77%, 50%, so on and so forth. Sometimes this will be all the way to 100, and then you do some quick math and add up all of the peaks. But that is very rare. Most of the time, they'll give you the height in percent abundance, and then they'll even label the peaks for you because it's really hard to read this here. We know this is 50, we know this is 20, but then is this 25, is this 24, is this 24.5? That can become a little more uncertain. Now the x-axis is what we call the mass to charge ratio. But because all of the atoms or isotopes are made to have a +1 charge, if you do a ratio between 1 and the mass of the isotope, it just gives you the mass of the isotope. So the x-axis is just the mass of the isotope. Even though we call it the mass to charge ratio, since the charge, Z, is 1, then it's just the mass of the isotope. So you can see here, this is an isotope with a mass of 10. Now it's probably 10 point something because it is an isotopic mass. 10 would probably be the mass number. 11, again, mass number, with the isotopic mass being 11 point something. But if they're not given the isotopic mass, then we use the mass number and vice versa. Now, what do the peaks themselves represent? The peaks themselves represent an isotope. So how far on the x-axis this isotope is going to tell us which isotope we're looking at. So mass number 10, mass number 11 isotope. And then how high the peak is tells us the abundance of that isotope. So we can read this as each peak being one isotope and then just getting the mass number from the x-axis and the percentage from the y-axis. Again, if you're given the actual isotopic mass, we will use those for the math, but if we're not, then we can just use the mass number as it's a really close approximation. Now that we're looking at this, the common question you will be asked is, what element is this? And sometimes you won't have to obviously read the y-axis, they'll give you the data. So here we have two isotopes. We have an isotope with a mass of 10, and again, that's the mass number, but we use it if we don't have the actual isotopic mass, and a percentage of roughly 23. And they'll usually tell you that percentage because, again, reading that y-axis, all of this is very hard. And then we have a second isotope with a mass number of 11 and an abundance of roughly 77%. So by looking at these two, if we wanted to know which element we were looking at, what we would essentially do is find the element's atomic mass and compare that to the periodic table. Whichever element the atomic mass is closest to that we calculate, that's the element we're looking at. So here, what we will do is we will use the equation. We have, again, a mass number of 10 for this isotope with a percentage of 23. So we will multiply those two because remember the equation, a percentage times mass number. or isotopic mass if we have it. And then we have the second isotope here, the taller of the peaks, which has a mass number of 11. And again, if we had the isotopic mass, we'll use that, but we don't, so we use 11, times 77%, which is the height of the peak. And because we're using 23% and 77% instead of 0.23 and 0.77, we will do all of this divided by 100. So each of the parentheses represents one of those isotopes. This is the first one. This is the second one. And we're going to divide the addition of both of those multiplications divided by 100 to get the atomic mass, which is roughly 10.77 AMUs. And again, we're dealing with atomic mass, so this is going to be in AMUs, not in grams per mole, which we'll do later when we get to the mole. If you wanted to do this as a decimal form without the divided by 100, then here's what we will do. We would, let me grab this, and we'll do it in pink here. We will do that 23% as 0.23 instead of 23% times that 10 isotopic mass or mass number, depending on what we're given, plus instead of that 77, we'll do 0.77, which is the decimal version of the percentage, times 11.00, which is the mass number, or again, isotopic mass if we have it. And then we will get the same answer, which is 10.77 AMUs. We will not divide this by 100 because we already did that when we divided the decimals, or the percentages, by 100. All right? So that's the other form of this equation, or that way we can form or show this math right here. But in either case, what we would end up doing is we will grab that atomic mass that we get and we will compare it to the atomic masses on the periodic table. Now, if we look here, we have a little section of the periodic table. We have boron, carbon, and nitrogen. Carbon and nitrogen are too far from the 10.77 AMUs, but boron is not. Boron's atomic mass is 10.811 on the periodic table, and that is close enough to make it our element. So this is the mass spectra for boron. Do not expect these answers to give you the exact atomic mass. They will be close, it will be approximations, because there's obviously error in data. The masses on the periodic table have been accumulations of massive amounts of data throughout time and different labs, whereas you're doing it based on one set of data. So, but 10.77 is closest to the atomic mass of boron, because carbon is too far up. It's a lot bigger of a difference. The beryllium, which will be the next one down, is around 9.18% or 9.18 AMUs, so that's too low. So boron will be the best candidate for our answer. So let's try it again, but realize that not every element is only going to have 2 isotopes. Some elements have massive amounts of isotopes, 6, 7, 8. There are even elements with 10 different isotopes. So let's look at this particular element. Now we can tell just by looking at these isotopes numbers, mass numbers, that this is a much heavier element. It's in the 90s for its atomic mass. And we can also tell that this mass will be closer to around 90 or 91 than it will be to 96. Why? Again, elements with higher abundances, so peaks that are higher, are going to be more influential to our atomic mass than element or isotopes with a lower abundance. So this is like the 96 isotope here. So because of that, we can actually visually tell that the atomic mass of this particular element, it's going to be closer to around this area. Oh, let me make that a little better. It's going to be closer to this area right here, because between these 2 isotopes, they have more percentage than all 3 of these put together. So that mass is going to skew closer to that isotope, to that one with the highest peak, because the other ones are not even close. Now, will it be exactly 90? No, it's going to be a little bit farther towards the right, somewhere along this line, because these do pull that average towards the right. just not as much as this 90 pulls it towards the left. So that, be careful with those, because that could be the prompt for a paper 1 question where they give you the mass spectra, and without doing any math, you could figure out what the right answer is by just looking, okay, which one has more abundance, which one's going to have more influence, so it should be closer to that. Because if they gave me something around that, so like 90.5 or 90.7, and then all the other answers are 94, 96, 95, then I can, without doing any math, tell that that 90.5 or 90.7 answer is going to be the correct one. But let's actually do the math here, because you will have to in paper 2 questions. So here we have a few different isotopes. We have the mass number 90 isotope with a percentage of around 51.5. And again, they'll usually give you the percentage numbers. We'll have the isotope at mass number 91 with 11.2% abundance. A 92 isotope with an abundance of 17.1%. A 94 isotope with a mass number isotope with a percentage abundance of 17.4%, and a 96 mass number isotope with an abundance of 2.8%. Again, these are the mass numbers. If they gave us the isotopic mass, we will go ahead and use them. But because they're only giving us the mass numbers, then we will use those instead. So what we have to do here is, remember, we're going to multiply the mass number of the isotope, or the isotopic mass if it's given, times its percentage, and then add all of those multiplications up for each isotope and divide by 100 if we're using the percentage itself. If we're using the decimals, then we skip the divided by 100 part. So here our math will be 51.5 times 90, which will be for this red isotope, 11.2 times 91, which will be for this green circled isotope, 92 times 17.1 for the blue circle isotope, 94 times 17.4 for the purple, and 2.8 times 96 for the yellow. Once we multiply all of those, we add them all up, and because we're using the actual percentages like 17.1 instead of 0.171, we're going to divide all of this by 100 to get the atomic mass of this isotope, or this element, sorry, which is 91.3. Once we have that atomic mass of the element, we can then go ahead and compare it to those on the periodic table to figure out what element this mass spectra was for. So in this case, if we look at the periodic table, we have deuterium at around 88.9, which is close, zirconium at 91.2224, which is a lot closer, and then niobium, which is a 92.9, which is a little farther overshot for 91.3. So our best option here is saying that this atomic mass, is for zirconium, and that's our answer. Now, you will sometimes have to use this equation. Sometimes they'll have given you the atomic mass and then ask you for the isotopic mass of one of the isotopes. But at that point, it should be as easy as setting up this equation using X for the masses and then, or the percentages, and then going from there. But we'll look at that later. So this is what a question on the actual AS exam might look like. Now I'm going to put this is on the PowerPoint just because of spacing, but I'm going to bring up a better way of looking at this. Give me 1 second here. So this is our question here from paper 2. They give you a percent abundance, and see, we can tell here we have those percentages at the top of each peak. What this does is that it makes it easier for you to not have to pull out a ruler and try to guesstimate what these abundances are based on this very lacking y-axis, which only has every 10 marked. So they give you the abundances, and it says the relative atomic mass of an element can be determined using data from its mass spectrum. The mass of spectrum of element X is shown with the percentage abundance of each isotope labeled. So this B part is essentially explaining what you're looking at. You're looking at the percent abundance, the mass spectra of element X, and they don't tell you what the element is because they're probably going to ask us for it. And they're telling us that these numbers on top of each on top of each bar are the percent abundance. So, if we read the question, use the data in the mass spectrum to calculate the relative atomic mass of AR of X. So they're asking us to calculate it. Give your answer to 2 decimal places, which is very important because they want you to use a specific number of decimal places. And if you don't, you will lose out on points. And suggest the identity of X. So we have to do all these things. We first need to do the math that we did earlier to figure out what the atomic mass of this element is. And then once we do that, we'll use that number to compare to the periodic table to then figure out which element we're looking at. So let's start doing that. I'm going to shrink this a little now that we have read it. Put it here in the corner. And we're going to do our math here at the bottom. Now, when we look at this, we'll use a different color. This is purple. Color purple. So when we look at this, right, we have here 1, 2, 3, 4, 5, 6 different isotopes. So we're going to have to do this 6 different times. Now I'm going to use the divided by 100 version of this, the full percentage version. If you wanted to use the decimal version, that will be perfectly fine and you will still get full points. So here we have our first isotope. We have a mass number of 74 with a percent of 0.89. Now be careful, this is already in percentage. This is not 0.89 as in 89%. This is 0.89%. So we're going to do here 74 times 0.89. That's our first one. Oops. Let me fix that 9. It's a little ugly. Plus, because remember, we're going to add these up. Now, what I would like to do is, as I do them, check them off to know that you already did it. Our second one here is 9.37% times 76 is the mass number. So 76 times 9.37%. And I don't like to put the percent sign so I don't get confused with whether they're decimals or not. I just put the number, so check that. Next one is 77, so plus 77 times, this one's 7.63%, 7.63. And again, check it off to know that you already did that one. Next one is 78 times 23.77, so plus 78 times 23.77. The decimal going to disappear on me. Plus, so we have the 78 already done. Next is the 80, which is the biggest one. So we can tell just by looking at this that the percent composition will probably, or the atomic mass will probably be around between 79 and 80. Because this 80 has the biggest pool, but there is a fair number of isotopes below it, only one above it. So this will be probably around 79 and 80, maybe exactly at 79 or around 79. But we'll look at that once we do the math. So we have here 80 times 49.61. And then finally the last one, so we check this one off. The last one's 82 times 8.73 being the percent abundance, 8.73. Once we do that math, we're going to add all of this and then divide by 100 because we're using the percentages, the 8.73, not the decimal version. Let me bring up a calculator here. So we're going to bring up our calculator, our scientific calculator here. We have 74 times 0.89 plus 76 times 9.37 plus, and again we use parentheses to separate them, 77 times 7.63 plus 78 times 23.77. 77 plus 80. Oh, nope. Let me 3219.55. 3219.55. I messed up the calculation there. So plus 80 times 49.61 plus, then the last one is 82 times 8.73. And then once we do that, we're going to divide by 100 because we use the decimals. And we get that our answer 79, and again, it says to 2 decimal places. So 79.04 would be the answer that we write down. So let's do it here. 79.04. And again, these are atomic masses, so it's going to be in AMU as the unit. So now that we know that it's 79.04 is roughly our atomic mass, we can bring in the periodic table and look for an element that has a mass of roughly, and I'm going to write it here so it doesn't go away, of roughly 79.04 AMUs. So let's look at our periodic table. And again, that's why I put that here. So 79.04. Remember that the periodic table is by atomic number, but the atomic masses are also kind of sequential. Some of them do flip. We're looking for something along the lines of 79.04. And if we look around here, we have in the 70s. So we have 79.0 for selenium, 79.9 for bromine. That's too far up. 79.9, 79.0 is a lot closer to 79.04. So this selenium is probably going to be our answer here. Arsenic is 74.9, which is too low. So selenium is probably our answer for this question. Se being the element that has a mass roughly around 79.04 that we calculated. And so let's go back to the PowerPoint, to the question itself. And we can see that the math that we did was right. We can see that the answer was 79.04 to 2 decimal places, and that the nearest element to that would be selenium. So you get 1 point for the correct numerical answer and getting the element right, and then 1 point for your work. So even if you were to get the wrong answer and the wrong element because you, let's say, didn't divide by 100, or because you forgot, or because you just messed up your calculation on the periodic table, on the calculator, you will still get at least 1 point here if you set this up correctly. Or let's say you find the right answer, 79.04, but you choose the wrong element. You will still get the point for your work. So that's something to keep in mind whenever we do this, is that even if you mess up, especially if it's more than 1 point, you can still possibly get the right, at least some of the points, even if you get the wrong answer in the final answer. So this is a type of paper 2 question that you could get. Now, like I said, skip the identification of organic compounds using mass spectroscopy. Because mass spectra can be used for 2 things, like I said at the beginning. It can be used for isotopes, but it can also be used for organic compounds. We are not going to use the organic compounds right now. This is the only chapter where we're actually going to skip a section, which is this section. And we'll revisit it in chapter 18 once we have done organic chemistry. All right? Well, that's it for section 3 of chapter 3. And I'll see you in the next AS Chemistry lecture series when we look at section 4.